Greetings all, my name is Yagemann, and today I'd like to share with you the work that my colleagues and I have been doing on analyzing the root cause of exploits in production systems. This is work done at the Georgia Institute of Technology along with my co-authors Matthew, Simon, Kennon, Brennan, and Wenke. So to start this talk, I want to discuss how exploits are detected in modern systems. Let's suppose we have a user program that contains a simple function with a handle procedure containing a while loop that reads data from standard in into a buffer, and then once all the data has been read, passes this buffer to a callback function pointer, and off the program goes. However, the astute viewer might already recognize that there's a bug in this code, which is that because the while loop doesn't account for the size of the buffer, it is possible for a sufficiently long input to overflow this buffer, corrupting local variables like the callback function pointer and allowing us to redirect the execution of the program to somewhere else, such as the exec function. And as it turns out, this is where existing defenses detect that something's gone wrong. For example, control flow integrity is able to recognize that this transfer shouldn't have been possible, and once this function goes off to interact with the rest of the system, systems for intrusion detection and prevention based on anomaly detection are able to recognize that this program is behaving abnormally and either flag the execution or outright halt it. However, notice that this is a symptom of the bug that arises after the while loop has already corrupted the callback function pointer. The reason why this is the point that gets detected is because it's the easiest point to do detection, because by this point the bug has manifested itself into a clearly observable behavior. Unfortunately, if we want to fix this bug and we only know its symptoms, we have to rely on techniques like input filters and function hardening, which are brittle and sometimes expensive to implement. Ideally, what we really want is for the developer to patch this bug. Unfortunately, in order for them to do so, they don't care about what the symptoms of the bug are. Rather, what they need to know is the root cause, which in this case is this while loop that's failing to account for the size of the buffer. So the question that this work focuses on is how do we get from a detected symptom back to its root cause? And as a side note, this example I walked through just now is a toy box that's designed to be simple. However, in our real-world evaluation, we find that the average distance between these points is about 11,000 basic blocks, so not something you would want to task a developer with doing by hand. Unfortunately, patching bugs post-mortem is a hard problem, and the reason is because the data available on production systems is limited. For example, if we look at crash dumps, they can be corrupted by bugs like overflows that overwrite useful values with junk data. System logs are useful for showing how the program interacts with the rest of the system, but doesn't tell us anything about what's going on internally. And while it's possible to record the concrete input that led to a symptom, sharing it with developers can raise privacy issues or concerns, and reproducibility is a serious problem due to non-determinism and environment differences. And in short, prior work has shown that developers tend to ignore or under-prioritize bugs that they don't understand, instead preferring to focus on the ones that they do know how to fix, which poses a problem for us. So in this work, we propose a solution called ARCUS, which stands for Analyzing Root Cause Using Symbex. And the key idea of ARCUS is to use what-if questions to test the impact of particular inputs on the satisfiability of security violations. In more details, the way that ARCUS works is we propose a series of vulnerability class-specific tests, which if satisfied are indicative of a bug, and in this work we implement tests for buffer overflow, use after free, and other common memory corruption vulnerabilities. Then at runtime, if a user program is flagged, we review a control flow trace of its execution, reconstruct intermediate symbolic states using symbolic analysis, and then we see if any of these states satisfy one of our vulnerability tests. And if so, we use this to generate a root cause report that can then be given to the developer, containing the location of the root cause, and even going so far as to propose a preliminary patch that the developer can then refine. However, you may be asking at this point, how can you collect control flow traces on a production system given its performance constraints? Well, you may have heard over the past few years the saying that hardware is the new software, and this is certainly true in the case of commodity processors. For example, if we look at a modern CPU from companies like Intel and AMD, we see that these days they have fairly robust tracing facilities that can record very low-level details, such as architecture events, cache events, power events, and particularly interesting for this work, control flow events. As prior work has shown, we can record the entire control flow of user space processes with only about 7% overhead thanks to this hardware assistance. So to show in more details about how ARCUS works, I want to walk through a real-world example using a CVE report in 2018. In this case, we have a Linux program that can incur a stack overflow given a sufficiently long command line argument. As a side note, for this example, I'm going to walk through the source code for clarity, but the real analysis that ARCUS does is directly on binaries without relying on source code or debug symbols. So the reason I picked this example is because we can understand it based on a single function, shown here. If we wanted to naively do a symbolic analysis on this to find the bug, we would start by symbolizing the inputs, namely this hname buffer, and initializing our local variables like so. However, before long, we would probably hit this for loop at lines 8 and 9 and run into a well-known problem with symbolic analysis known as state explosion. Namely, because we don't know how long this input is, we don't know how many times we should iterate this for loop in search of bugs, and in theory, we could do it forever. Fortunately, ARCUS completely sidesteps this issue because we have the trace from the processor, which tells us that the execution that led to the symptom requires us to take this branch and then iterate on the loop exactly 312 times. And by the time we reach the end of the function, sure enough, we see that the return pointer has been overridden with one of the symbols from the user input, which satisfies one of our vulnerability tests, namely for stack-based control flow hijacking. So now that we have this state that satisfies one of our tests, how do we turn this into a root cause? Well, we have all the intermediate states leading up to this point. So at this point, ARCUS can ask the what if question, which in this case is what if we didn't corrupt this pointer? Well, if we didn't corrupt this pointer, we would have to go back to a previous state immediately before the pointer was overridden, which places us inside the for loop. And in order to avoid overwriting it, rather than iterating the loop another time, we would have had to exit at this point. And then sure enough, by the end of the function, we see that the return pointer is preserved. So what is the key difference between these two states, the one that overwrote the return pointer and the one that didn't? Well, it turns out that in the one that did overwrite it, at this particular offset in the input, there's no close bracket, whereas in the one that did, there is a close bracket. And these constraints directly contradict each other. So from this contradiction, we can devise that as long as we enforce that there's a close bracket by this offset within the input, the bug will not occur. And indeed, this does fix it. So to evaluate this approach in the real world, we devised 27 exploits targeting 20 real Linux programs. And ARCUS was able to detect the root cause in all the cases. Also, in cases that have already been patched by developers, we compare ARCUS's root cause or preliminary patch against the official patch and find that they're completely consistent in all cases. Perhaps most interesting, though, is in the process of analyzing these known vulnerabilities, ARCUS was actually able to uncover 4 new 0 days, which were severe enough to lead to the issuance of 3 CVEs that were then patched by developers using ARCUS's reporting. So if you think these results are interesting, I invite you to take a look at the paper where we go into a lot more details. For example, on the vulnerability classes that I didn't talk about here, more details on how ARCUS interfaces with control flow tracing, and particularly Intel processor trace, interesting case studies such as how ARCUS was able to find 0 days from analyzing known vulnerabilities, and additional experiments I didn't cover here. And with that, I'd like to thank you for your time. My contact information is on this slide. Also, the source code and evaluation dataset for ARCUS is completely open source, available at the provided link. And once again, I'd like to thank my co-authors for their contributions on this project. Thank you.